everyone. I think we can start. So, exciting.
Got it.
Today we're very happy to have Mark van Raamsdonk. Mark is a professor at the Department of Physics and Astronomy at British Columbia. Sorry about that. Difficult names.
Columbia's in there somewhere. For some weird reason.
Somewhere in the United States. Mark obtained his PhD in theoretical physics at Princeton University and then went on to do a postdoc at Stanford. He is interested in quantum gravity, its connections to quantum information, space-time entanglement, and he has made crucial contributions to the way we think about the emergence of space-time in holography. And today we'll talk about cosmology via holography. So thank you.
All right, well, thanks for coming. Thanks for the invitation to speak. And so, yeah, I'm interested to tell you all about some research that I've been doing, I guess, over the past roughly 5 years. I've started to be interested specifically in cosmology and maybe how to apply some of the recent progress in quantum gravity to that direction, which is like obviously one of the big reasons why we would want to understand quantum gravity in the first place would be that I think most people think you would need that to understand the Big Bang. If you wanted a sort of complete mathematical theory of cosmology, then that has the Big Bang in it, then probably you really need a quantum gravity theory. There are other reasons why you would want a quantum gravity theory or to think about cosmology from the point of view of quantum gravity. Like a lot of times within cosmology, we just use effective field theory, and that's fine to understand most of the physics from an instant after the Big Bang up until now. But we could imagine having some guidance from quantum gravity for questions like, well, which effective field theories are natural or possible? What are the possibilities for dark energy, or what would be natural kinds of explanations within effective field theory for dark energy or dark matter? Is inflation sort of a natural thing to happen? Is that something that you can actually get out of a more complete quantum gravity model? And so I think there are various things that we could possibly learn. And so my background is in string theory and mostly holography, since my first research paper was the same year as I think the completion, like, so 1997 to me is when we first had complete models of quantum gravity. So like string theory existed before that, but it was more like a set of rules to calculate some things. But with the ADS-CFT correspondence, then we have a statement that at least certain full theories of quantum gravity in special kinds of spacetimes, asymptotically ADS spacetimes, these theories are supposed to be completely defined or equivalent to much more ordinary quantum mechanical systems without gravity. So that was a major advance. So at least for understanding gravity with a negative cosmological constant, this is great, and there's been tons of progress since 1997. In terms of cosmology, an interesting thing happened a couple of years after 1997, which is that supernova observations indicated that at least recently our universe is accelerating in its expansion. And well, the simplest explanation for that in terms of Einstein's equations is just to add a small positive cosmological constant. And that's been the standard simplest model, or the standard model of cosmology just assumes that there is such a small positive cosmological constant. We'll review other explanations for this acceleration that will be important in this talk. And so in terms of the dealing with cosmology and string theory, I think what happened after this was that people started thinking about how do you explain a small positive cosmological constant within string theory. So kind of taking the assumption that that's what we're looking for, is this small positive cosmological constant. And then people tried to argue that this maybe could arise dynamically in the context of string theory. The idea was that string theory perhaps had many, many solutions, many different vacua with lots of possible cosmological constants. And Busso and Polchinski and maybe others at the time had the idea that if you were in some pre-existing vacuum with, say, a larger positive cosmological constant, then you could dynamically form these bubbles of space with smaller positive cosmological constants. And then the idea was that you have this bubbling multiverse, and then eventually through this dynamics, there would be regions of the universe with a small enough positive cosmological constant that structures could form and life could evolve, and we could be there to observe it. So there was this anthropic explanation for the small positive cosmological constant. At a technical,
that's a finite number of regions, right? Wasn't that there would be finite regions that would have lambda greater than 0?
well, there would, I mean, it could be an infinite multiverse, but then in certain regions of space, it's a little bit funny because they could be finite from the outside, but infinite from the inside in a sense. So it's some interesting geometry, but yeah, depending on how you do the time slicing. So that was the basic idea. But then at a technical level, that required you to like find these vacua of string theory. So you wanted to show that there was some very, very dense set of vacua of string theory with all sorts of different possible values of the cosmological constant, including these small ones that would explain the observations. And this was kind of controversial about whether these people tried to write down solutions, but there were arguments about whether they were really under technical control, about whether they existed. And at the same time, there were arguments, say by Strominger and others, or attempts to extend this holographic picture to positive cosmological constant. But I would say at the end of it, back then, there weren't really any kind of satisfactory models of quantum gravity with a positive cosmological constant like we had for the negative cosmological constant. Okay. And so then jumping forward, that brings us to the present, where maybe the mainstream viewpoint for how would string theory perhaps describe our universe is pretty much the same. That maybe we could explain the observations by there being a small positive cosmological constant, and maybe that emerges from some dynamics in a bubbling multiverse. People are arguing about whether these vacua actually exist or not. And there have been recent efforts to extend the holographic picture to positive cosmological constant, like just a little bit different than previous efforts. But I would say so far, none of them give you any kind of a fully satisfactory model where you could say, okay, here's a mathematical system, and this thing describes gravity with a positive cosmological constant. Okay. So it feels a little bit like the progress has been very slow in understanding how to do positive cosmological constant physics in the context of string theory and holography. And so I guess I want to advocate for a different plan, which is a little bit more modest, where instead of jumping right to positive cosmological constant and trying to understand that physics within the context of string theory or holography, let's start from what we know, which is quantum gravity with a negative cosmological constant. We understand that at least for certain classes of spacetimes, spacetimes that are asymptotically ADS, then we can understand quantum gravity in these spacetimes via some dual non-gravitational quantum system, via some conformal field theory. So it turns out that these exact same gravitational effective field theories that everybody is talking about in that context, you could just find other solutions of those same gravitational effective theories that are cosmological solutions. And so why don't we just try to understand the physics of cosmology in those universes based on these effective field theories that we already understand how to describe in other contexts. Okay, so can we
So what do
look
you mean by cosmological solutions? Do you just mean that you are able to provide the initial conditions for inflation?
Yeah, so
Okay.
I'll tell you
Yeah.
more in a second. So yeah, maybe in one slide I'll get to what I mean exactly by the difference between these. But basically homogeneous and isotropic. So these ones are not homogeneous and isotropic. Okay, so let's just try to do that. And then, if we could describe cosmology with a negative cosmological constant, then maybe that'll teach us general lessons about cosmology, and maybe it'll indicate how we should learn about cosmology in other contexts, say with a positive cosmological constant. Okay, and just as a comment, I mean, this was really the right strategy for black holes. Like if we always knew that the black holes in our universe are not ADS black holes, but we didn't discover holography and then discard it and just keep trying to understand black holes in asymptotically flat space-time or in de Sitter. We made a huge amount of progress since 1997 on understanding black holes, but also quantum gravity more generally, by studying black holes in ADS space-time. So we used ADS-CFT as like a laboratory to just understand quantum gravity, to understand the question of black holes and what are the quantum aspects of black holes. And then like recently, we're understanding lots of lessons about more general black holes and the black hole information problem based on that work. Okay, so the plan of the talk is then I'll describe a little bit more about what are these cosmological solutions, how do they differ from the kinds of spacetimes that we usually understand in holography. And then I'll try to explain how these cosmological spacetimes or the observables in these spacetimes might be extracted from some CFT physics. Okay, so how could you use holographic tools to understand cosmological physics? And then I'll kind of talk about what are some of the lessons that we learned. Okay, I want to give a little bit of a spoiler, like just in case you fall asleep later in the talk. There was a surprise that happened in the last few years, at least for me, when studying this research program, which I thought was going to be mostly about non-realistic cosmologies. Okay, and I was going to be happy with that, and we were going to learn things like we learned with ADS black holes. One of the things that seems to come out of studying these negative cosmological constant cosmologies using holography is that actually, generically, these cosmologies can have phases of acceleration after the Big Bang. And that is due to the fact that in these models, you would typically have some time-dependent scalar fields. Okay. And those time-dependent scalar fields could at some time have a positive value of their potential that acts as a positive cosmological constant. And then later, they could decrease their potential energy as they move towards the negative cosmological constant that you can think of as the minimum of the potential for these scalar fields. Okay. So the cosmologies that we end up studying here are actually more realistic than I would have expected going into it. And well, whether or not they could be actually realistic is, I'm not sure yet, but I think if you're just more interested in things that could be observationally relevant in the nearer term, then maybe you could also pay attention in the talk. All right, so starting with 1997 and going forward from that, we had this holographic model of quantum gravity. What does that mean? So you have a more or less ordinary non-gravitational quantum system. You could imagine like a two-dimensional sphere, and you can imagine some exotic material that lives on this two-dimensional sphere, and that obeys ordinary quantum mechanical evolution rules. You have various states of that system, and the idea is that each state of that non-gravitational system is encoding somehow the physics of a quantum gravitational system. And that could be many different possibilities, but all of the states would correspond to gravitational states where asymptotically it's just empty. So asymptotically, you have negatively curved space with nothing in it. And then in the middle, you could have lots of interesting things, black holes or gravitational waves or radiation, matter, whatever. All right, so we can kind of think about the evolution of these states as being dual to the quantum evolution of the states over here, and ask lots of interesting questions, and people have learned a lot about black holes doing that. But it's quite a bit different than what we do in cosmology. So in cosmology, we assume from the start that we're wanting to look at a universe that's filled with stuff. Okay, so we assume homogeneous and isotropic matter at large scales, and as a result of that, the entire universe is dynamical. So typically we start from a big bang, there's expansion, our observations suggest that's currently accelerating. And so that's kind of different from these spacetimes. Okay.
Mark,
yeah.
So already in the early 2000s, 2004, 2005,
Yeah.
there were these Coleman-DeLucia type constructions with a scale of basically essentially saturating the BF bound, where they would have this the Big Bang and Big Crunch cosmology, and it would have an expanding phase and a contracting phase, but asymptotically ADS, right? And they concluded that the dual theory, but it goes sick like very far past the very far future.
Yeah.
Dual to the singularity. So, but those are asymptotically ADS.
Yeah, I mean, I think so. Those cosmologies, okay, if I'm remembering correctly, yeah. I mean, I think they were not really homogeneous and isotropic in the bulk.
They were there. So they were just ADS FRW. So like open FRW in the bulk. You have the FRW cone, and then you have the rest of it is kind of you can slice it into the sitter slices if you like.
Mm-hmm.
And then on the inside of the cone you just have ordinary isotropic FRW. Just an open FRW, so it has an expanding phase and a contracting phase. I mean, I think if I understand your constructions, you're going to be doing something different, but
yeah,
I do think that there were efforts, right, to understand ADS holography, ADS cosmology, because they do have those constructions. It's just that the CFT would go sick in the far past and in the far future, like the Hamiltonian was unbounded from below if you evolved too close to the singularity.
Okay, so I do remember some of the details, but there was some time dependence in the Hamiltonian
for the CFT. Yeah, because they had to turn on the scalar that was it was saturating BF bound, so it was okay from the bulk perspective, but somehow the Hamiltonian was unbounded from below in the far past.
Right. Okay. Well, we should talk about that. I should review that work. Yeah. Okay. So I think the kinds of what I have in mind for talking about cosmology is just to take the same. So there's some gravitational effective theory that comes out of this. Given the CFT, there's some spectrum of operators in the CFT, and then the ADS CFT dictionary usually relates the operators that you have in the CFT to the fields that you have in your gravitational effective theory. And correlation functions of the operators can tell you about the Lagrangian for the fields. And so I'm imagining we're starting with some particular CFT, that there's some particular gravitational effective theory that we could study asymptotically ADS spacetimes for. But we can also take that gravitational effective theory and consider a homogeneous and isotropic solution where we add matter or radiation, and then ask what happens to that space-time. And so typically then these kinds of cosmologies are Big Bang, Big Crunch cosmologies. So with a negative cosmological constant, what happens is that you would have a Big Bang, the matter and the radiation like dilute, and so the cosmological constant term in the Friedmann equations becomes more and more important. Because it's a negative cosmological constant, that will eventually cause the universe to sort of turn around and recollapse, so that you get the big crunch. And if you just sort of solve the equations with matter and or radiation, you get some nice time symmetric solution, something like that. Okay, and so one of the challenges then is that if you have that kind of a solution, then at least the ones that I'm considering are not asymptotically ADS. And so we can kind of understand that from the following picture. So this is like a space-time diagram for just pure empty ADS. And so there is, in this case, before I add any matter or radiation, so there's a set of coordinates that look like FRW, and they describe a certain patch of ADS like this. And then what I could do is just imagine adding a bunch of matter or radiation on a time slice and make it homogeneous and isotropic, and then evolve that forward. And then what happens is that this whole asymptotic boundary kind of goes away, and you end up with a big bang and a big crunch. And this is like your observer in the middle of the cosmology. And so the part of the space-time that indicates that there's some CFT. So usually we associate the geometry that the CFT lives on to the geometry of the asymptotic boundary in ADS CFT. And here the asymptotic boundary is just on. And so it's not really clear how we should proceed in studying this thing holographically. Okay. So I'm going to mention two possible ways forward. Okay, and so the first one is something I've worked on more recently, and that's just to take the idea that if we don't put matter and radiation all the way out to the infinite boundary, let's say we just put a finite amount of matter and radiation inside a bubble of some radius, okay, which could be anything less than infinity, and then we can assume this is homogeneous and isotropic at the initial time inside the bubble. And then if we just take empty space-time outside of the bubble, then it's actually possible to find a solution where this is just patched on nicely to an asymptotically ADS Schwarzschild black hole solution. In fact, you can have an arbitrary combination of matter and radiation, and then to get them matching, it's actually sufficient just to have a shell of dust with some density. And then you can solve the Einstein equations and junction conditions. And so you find a solution where this interior region of the FRW space-time is patched onto an exterior region of an empty Schwarzschild ADS space-time. And then the space-time diagram for the entire space looks like this. Okay, so there's like a shell. Inside
Lambda here is still less than 0, right?
Pardon?
What about lambda?
Yeah, lambda is still, I'm still thinking
Yeah.
lambda less than
Okay.
0 here.
Okay.
That's right. This idea actually goes back. There was a paper called Inflation in ADS CFT by a long list of authors that I will not try to remember, including Schenker and Maloney and Cubany, Ranganani, Rob Myers. I don't know. I'm sure I'm missing someone. So they have the idea of doing this, but with a positive cosmological constant inside. But here I'm just imagining this negative cosmological constant cosmology. Okay, so you have these solutions, and they are asymptotically ADS. Okay, and so
Just a quick question.
Yeah.
So how do you get around the positive energy theorem? Like if you take the mass of black hole to 0, so you're just embedding this in pure ADS?
sorry, I'm embedding it in vacuum, so it's a positive mass Schwarzschild.
Okay, you definitely, okay.
So
okay.
I'm just saying that there's no stress energy tensor outside of the bubble. So there's matter and radiation. Inside, there's a stress energy tensor on the shell, and then outside, it's just the vacuum Einstein equation.
And then
So you get a positive mass Schwarzschild.
So the industrial, does that reach the asymptotic boundary eventually, or does it go into the singularity?
It goes into the singularity.
Okay, but then that makes the black hole grow, so it's registers. Okay.
Yeah. So I think I sort of addressed that a little bit. And so, okay, so one interesting thing about this is that if you imagined an observer in the middle of the cosmology, so you could make this, because there's a big bang and a big crunch, there's only like a finite region of this universe that the observer could ever interact with in the whole history of the universe. There's only a finite region where the observer could say receive any signal from or send any signal to, and you could embed that entire region inside one of these black holes. And so if all you care about is the physics of one observer in a homogeneous and isotropic cosmology, then it seems like perhaps this is sufficient to include a description of all of that physics. Okay, so the idea is that, well, if I could find a CFT description of these kinds of spacetimes, then I could talk about what is the CFT description of the cosmological physics that is experienced by that observer. And so that's actually pretty interesting from the point of view of ADS-CFT, because this cosmological physics experienced by the observer is generally behind the horizon of the exterior part of the spacetime, behind the horizon of this Schwarzschild black hole. And that's sort of a really interesting and challenging part of ADS-CFT research, to understand how do you describe the physics of behind the horizon of black holes using the CFT. And people are like Netta are making interesting progress on that in recent years. Yeah.
Sorry, just to make sure. So here you are thinking about cosmology in the fog, but not Brownian cosmology.
Yeah, that's right. In this case, it's actually, say, 4D cosmology here, and then a 4D black hole, and then a 3D CFT on the boundary. There's other approaches where you have a 5D bulk, and then a 4D brane, and a 4D boundary theory.
But that's another stuff.
That's a different story. Yeah, different story. Yeah. Okay. Yeah, so like one basic check, one worry that you might have about this story is that somehow there isn't really, well, there might be a gravity solution, just classically, there might not actually be a valid CFT state that describes the physics of such a solution. There are sometimes worries about a bag of gold paradox, if somehow the entropy of all of the stuff that you want to describe in the cosmological space-time, if that were to exceed the entropy of the exterior black hole, then you would maybe conclude that your CFT doesn't have enough states to actually be describing that cosmological physics. And so you could do some basic checks, and what you find is that in most cases, the black hole entropy that you calculate in the usual way from the space-time does exceed the entropy of the cosmology. And so it does seem like this approach could give you some practical way to embed cosmological physics in ordinary holography.
Is it stable under perturbations?
Is
Homogeneity. The inside's not homogeneous, whether it's not fractions.
so the inside, I could take it to be locally homogeneous and isotropic. So there should be the usual cosmological perturbation theory.
That's an approximation on the exact statement. I'm asking if it's stable under perturbations.
Well, I think the usual cosmological perturbation theory would be the set of equations that you wod use to analyze the stability.
Yeah, I'm asking if this configuration is stable.
Right. So I'm saying that that as far as I know, you will get the usual growth of perturbations that you would have in cosmology. So
I'm asking if you're going to maintain your spherical symmetry and your homogeneity under perturbations. It's not obvious to me that you do.
So yeah, I mean, we haven't done a complete linear perturbation analysis for the whole space-time. Right. So one could worry about say what happens with a shell. I think if you're just worried about the physics of the observer here.
No, I'm worried about the shell.
Yeah, okay. So one could worry about the shell. Yeah. yeah, I mean, I guess you could choose to decide that it's spherically symmetric here and ask what happens.
And also,
I'm not sure what
centering
would-
it in the center of ADS.
Pardon?
Do you have, it's also, is it important where you put this patch of FRW in the ADS?
Well, I mean, ADS is homogeneous and isotropic. So,
Not when you put this thing in.
right, once you put it in, that
Right.
defines a
That's gonna
center.
Make a difference.
So you could move it around, and that would be something that you could do using the symmetries of the CFT. So you would have one solution where you'd have the bubble in the center, and then if you applied some symmetry generator, then you could have this whole bubble be oscillating around in
But then
ADS.
you also have to transform the bubble,
So
your spherical shell.
yeah, the spherical shape, yeah, so that's right, under, there would be, I mean, it's just a different set of, from the bulk perspective, it's just a different set of coordinates. From the boundary perspective, you would actually have different states that would correspond to physically equivalent things happening in the bulk. Sure. Okay, so I want to focus though on I think maybe a more natural approach. This is a little bit ugly because we're trying to describe something homogeneous and isotropic, and then the first step is to kind of break homogeneity and isotropy by assuming that there's like a boundary to the region of cosmological space that we're studying. And so I would prefer not to have to do that, although you could imagine taking that previous construction, taking some kind of a limit where the bubble ends up becoming infinitely large. So instead, the other approach starts with an observation that even though the Lorentzian spacetime doesn't have any asymptotically ADS region, if you consider analytically continuing the time coordinate, so consider the Lorentzian time, and then take the geometry here. This is just an example. If you had radiation plus negative cosmological constant, if we analytically continue to look at imaginary values of the time, just formally in this solution, then the imaginary time slice here actually is an asymptotically ADS spacetime. The imaginary time slice is a spacetime that actually has two asymptotically ADS regions. Sometimes we describe this as a planar asymptotically ADS wormhole geometry. And so that is hinting that maybe even in this case where you have homogeneous and isotropic cosmology, say on infinite flat slices, there's still some kind of underlying CFT physics there. And so we'd like to understand what is this telling us? And so just to remind you, it is very common in quantum field theory and in gravity to consider analytically continuing the time coordinate and to consider the Euclidean version of a theory that you're interested in. In quantum field theory, when you study the Euclidean version of a quantum field theory, then that is a way to study the physics of certain special states of the Lorentzian theory. So the correlation functions of a quantum field theory on Euclidean space, if you analytically continue those things, you get the correlation functions for, or some of the correlation functions for the Lorentzian quantum field theory in the vacuum state. If instead you consider that Euclidean quantum field theory on a different space, on a space where this Euclidean time direction is a circle, then you calculate correlation functions in that Euclidean theory, then you analytically continue, and those define correlation functions in the thermal state of the Lorentzian quantum field theory. In gravity, then studying the Euclidean quantum gravity theory can also be a way to construct a state of the Lorentzian theory. So the idea of Hartle and Hawking is that you could come up with a wave function of the universe by considering a Euclidean gravity path integral where the wave functional evaluated on a certain 3D spatial configuration would be equal to an integral over all the different ways you could complete that, where you could have this as the boundary of some 4D configuration without any other boundaries. Okay, so that's the Hartle-Hawking wave function. And so from this perspective, what it suggests is that the relevance of this Euclidean picture would be as something that could construct a state for our Lorentzian theory. So it suggests that the right approach here would be to start with this Euclidean picture, find a holographic description of this Euclidean wormhole geometry, and then so kind of use holography to give a complete definition of this gravity path integral that describes this thing, and then use that to define a state of the Lorentzian cosmology. And so then in practice, the cosmological observables, like the evolution of the scale factor or cosmological correlators, one could compute them by starting with this theory, computing observables, and then analytically continuing to understand the physics in the Lorentzian theory.
What's the relationship of the two CFTs? Do they each correspond to a different part of the?
Yeah, so the Euclidean geometry that we get by analytically continuing this has these two asymptotically ADS regions. And so the idea would be that short distance physics of this CFT would correspond to the physics close to this boundary. And the short distance physics of this CFT would correspond to the physics close to this boundary. And I have to still tell you, what it is that would relate these two things. Okay.
Actually, I have a question.
Yeah.
So in asymptotically ADS standard
Yeah,
ADS CFT, we know we think that the path integral doesn't actually compute, correlators very accurate, doesn't compute overlaps, because it has this issue of the factorization problem, which you're leveraging here, by saying that you have a Euclidean wormhole. So how much confidence do you have that it's accurately computing, observables that are not self-averaging in the cosmology?
Yeah, I think I'm gonna address this a little bit. So yeah, it'll be important to say like exactly what are we doing from a CFT perspective to get this wormhole out, and what sort of averaging is there, and how do you interpret that averaging? Exactly. So yeah, I'll have some things to say presently. Okay, so so how do we holographically describe the wormhole? If we just had two Euclidean CFTs and they have nothing to do with each other, then we know what the gravity description of that would be. It would be two separate ADS spacetimes that have nothing to do with each other. And we could learn about that, but that's not what we're wanting to do here. So this is obviously got more in the construction than just having two Euclidean CFTs. And so in order to get something like this, there needs to be some relation between these two CFTs. And so some ideas that have come up in previous discussions of how do you describe wormholes in holography is that maybe it involves some type of ensemble of theories, or maybe it involves some kind of interaction between these two CFTs. And so I'll mention a few possibilities. So Maldacena and Maus quite a while ago considered the question of how do you describe Euclidean wormholes in quantum gravity, and they suggested that instead of just being dual to a single pair of CFTs, that somehow if you thought about a family or a collection of theories, and you thought about the partition function of the individual theories and then summed over this product of partition functions over all of the theories, so that would be a quantity that is not factorized between two different CFTs. And they suggest maybe something like this is the quantity on the CFT side that this wormhole physics is capturing. So this has actually been borne out recently in studies of 2D gravity. There are very explicit examples where we have wormhole solutions in JT gravity in a two-dimensional model of gravity, where we know that indeed those wormhole solutions are computing something like this, where we know exactly what the theories are. So we're summing over like a bunch of different theories, calculating this, we would call it an ensemble average of this product of partition functions. And so that would be the physics of this wormhole. This is a little bit unsatisfying for the higher dimensional cases, because in holography, I mean, we usually think of starting with some specific CFT, and so like n=4 super Yang-Mills theory, some very specific CFT, and it's not really obvious what you would mean by thinking of that as part of an ensemble of theories. There's not a clear candidate for there being a whole bunch of theories where that's just one element, and then we can sum over the theories. Yeah.
Oh, sorry. I think I'm confused by the ensemble argument here,
Yeah.
because if you continue this configuration to Lorentz signature,
Yes.
then it can be simply just embedded into the global ABS by taking a specific patch where there's no ensemble there, right?
Well, so the continuation of this to the Lorentzian theory was this cosmology that we weren't really sure how to describe in an asymptotic, like that wasn't asymptotic ABS.
Oh, I mean, like, if you're looking at the situation where there's no matter involved in this theory, then you can embed that into. I mean,
Do you want to analytically continue this direction or just some other direction to get a Lorentzian picture?
Oh, the Euclidean time direction.
Yes.
And then you have like continue that to Lorentz signature. You have a two-sided black hole. But for that two-sided black hole, you can embed that into global ABS by say you have.
Yeah, this is not something that continues to a two-sided black hole, or it's a little bit different than the usual. So maybe you have in mind just the usual ADS black hole.
And one of these is in the Euclidean past of the other. This is not the same as the standard Einstein-Rosen-Bridge.
Sorry. So like which direction is the Euclidean time direction?
Yeah, it's like this direction is the Euclidean time direction.
Oh, I see. Sorry,
Yeah.
I thought it was this direction.
Okay.
So, yeah.
Yeah, I mean, it's interesting to, if you have a translational symmetry in this direction, then you can analytically continue to get a Lorentzian spacetime that would be a traversable wormhole. Okay, and then you actually require there to be some interaction between the two CFTs. So, so I was going to mention that later, but yeah, for now, the simplest way to get something which is not factorized is just this kind of thing. This is the answer in some 2D gravity examples. I wanted to just mention a slightly more general thing that perhaps doesn't require us to have an ensemble of theories. So something that I've been thinking about recently is that you might be able to describe such a wormhole by starting with a single CFT and then just considering a certain ensemble of observables, and I'll give a specific example to illustrate that. So I've been talking with Alex Maloney and his student Viraj about the following thing. One of the most simple ways you could imagine to get a cosmological solution is just to have a whole bunch of heavy matter particles and just have those follow some geodesics in a space-time. And in 3D gravity, it's possible to write down some explicit solution where the heavy matter particles give you conical deficits. And so there's some completely explicit like 3D cosmology that I could analytically continue to a 3D wormhole. And in that example, what happens is that, well, these heavy matter particles, they just make it all the way out to the asymptotically ADS boundaries. And then this is actually something that is commonly studied in ADS CFT. The idea is that if you want to get one of these heavy matter particles in your gravity solution, you should just insert an operator with a large dimension at the point where the geodesic intersects the boundary. And so standard ADS CFT recipes would tell you that this space-time corresponds to something like this, something like the product of like partition functions with operators inserted on one CFT and then operators inserted on the other CFT. But this expression can't quite be right. This is just as bad as the two separate CFTs because it's completely factorized. And so the idea is that there's actually a natural way to make this into something that's not factorized. And that is to realize that if you have a certain heavy particle here, so there isn't necessarily just one operator that we would associate to that. So in conformal field theories, then any operator also has these various descendants, which is just like taking a field theory expression and putting derivatives in front of it. So there's actually a family of operators in the CFT that one would associate to a certain particle in the bulk. And one could imagine doing, instead of inserting one particular operator here and here, it would actually be more natural to insert a operator with an index and an operator with another index, and then to sum over those indices with something like a density matrix. Okay, so if we think about an actual particle in cosmology, it's likely to be some kind of a mixed state of various kinds of wave functions for the particle. I think I just, hopefully that'll come back. So if you want to get something more natural, like a bunch of mixed state particles in your cosmology, then you would actually be doing this kind of thing where you're inserting operators in the CFT and then having some coefficients there and summing over all the insertions. Okay, so this is something that gives you a non-factorized CFT quantity, but you don't have to start with a whole family of different CFTs. You can just start with one CFT, and then it's like a whole family of complicated observables. So that's kind of work in progress.
So those always exist? It's always possible to make that construction?
Well, yeah, this is, so in, CFTs, again, they just have a list of possible operators, and you can insert these operators. And if you want to, you can always just sum over the stuff you're inserting. So, yeah. So an interesting feature of this is that, like, somehow to get the cosmology at all, you have to be considering an ensemble of different possibilities. So you can't just, from this Euclidean picture, start with some construction that will give you one particular instance of cosmology where all the particles are in specific places. The only thing that you're actually able to construct in order to get the non-factorization that allows the wormhole, that allows the cosmology, you need to end up considering what in the cosmology is an ensemble of things. That's sort of.
And do you leave off the possibility that they can collide and merge and interact?
Well, this is my toy model, and of
You
course
leave that out, so that's excluded.
the
Construction.
it's not excluded in this construction. So in the motivating construction where I had this really simple cosmology where I had particles that are traveling on geodesics and some lattice, then I didn't have that. That was consistent. There was a solution. But the more general construction would be that I start with my CFT, I insert a whole bunch of operators on one side, a whole bunch of operators on the other side, and I sum over these things. And then I think in general, these would correspond to solutions where all the stuff is interacting. And, it will be complicated.
But the indices wouldn't be equal up on the top and bottom, because you could have annihilation of particles, you could have merger of particles.
Yeah, so
particle production.
I think I would want to consider something that's time symmetric here in order to have something over here that in order to get something that I can analytically continue to a real cosmology, then I should have some time symmetric construction here. Yeah. Okay. Oh, okay. I should speed up a little bit. So I'll just like briefly mention maybe even a simpler idea, like how do you get this wormhole? The ensemble story is a little bit fancy. Maybe a simpler version of this would just be to say, okay, if I have two separate CFTs that are not interacting with each other, that's dual to two ADS spacetimes that are disconnected. How do I get something connected? Well, just like make the CFTs interact somehow. And so in a series of papers, we discussed that by coupling two CFTs by higher dimensional quantum field theory with perhaps relatively few degrees of freedom, you could have a physical system that in the UV is mostly dominated by the CFT physics of these two separate theories, but in the IR could be very much different because of some renormalization group flow, and where there could be strong correlations between the two sides of things in the infrared. And so that kind of general physics suggests that perhaps the dual of this kind of a theory could be something where you have the two asymptotically ADS boundaries, but then there's only, it's not possible to distinguish there's not a separation of degrees of freedom in the infrared once you couple these things. And so that would correspond to having the wormhole, the connected geometry. So that I think is conceptually simpler. If I were to integrate out these auxiliary degrees of freedom, so imagine just doing the path integral, integrating out these 40 degrees of freedom, you would actually formally get something that looks just like this in the end. And so this is maybe a special case of the previous thing. Okay, so I definitely want to get to the story about the scalar fields, so we can start asking, let's say we are able to use one of these methods to holographically construct the wormhole, and so then what is the physics of these cosmologies? Can we say any generic things about the physics of these cosmologies? And so one of the most interesting features is that I think a phase of acceleration is actually rather generic in these constructions, despite having a negative cosmological constant. Okay, and so so I mentioned that the fields in the gravity theory and these holographic dualities, they're related to the set of operators that you have in your CFT. And so when we think about conformal field theories, there is typically some way to perturb those theories so that they flow by an RG flow to some other infrared theory. So we kind of think of conformal field theories as being special field theories with extra symmetries, but that you could then find some relevant operator in the theory, and if you want, you could add the relevant operator, and then it would flow down to another theory. So n equals 4 super Yang-Mills theory has 6 of these relevant operators. When you have a relevant scalar operator in a CFT, then the dual gravitational effective field theory has a scalar field whose mass squared is negative. And this is something that is allowed in asymptotically ADS spacetimes, as long as the mass squared isn't too negative. And there's this relation between the mass of the scalar, this is the cosmological scale or the ADS scale, this is the dimension of the operator in the CFT. And what it says is if the dimension is of order 1, then the scale of this mass, okay, which is related to the scale of the derivatives of the scalar potential, then that is ADS scale. Okay, so here I'm trying to represent for one of these scalar fields, what does the potential look like? And so the fact that it's a relevant operator and that the corresponding mass squared is negative means that starting from 0, the potential goes downwards. And typically we would expect there to be some interaction terms for such a scalar field. And if the theory is stable, terms like phi to the 4th shouldn't go to negative infinity. So a typical thing would be for there to be a negative part near the origin and then some interaction terms to turn this thing positive as you go to large values of the scalar field. Okay. And so in generic solutions of with asymptotically ADS boundaries. Okay, so these scalar fields with a negative mass squared, they typically don't stay at 0 all through the space-time. They would typically be, say, 0 at the boundary, but then evolve as you go inwards in the space-time. And so in the kind of most generic solutions of the type that I've been talking about, then you'll have a spatially dependent scalar in the Euclidean picture, okay, that will vary. The scale of variations is just the ADS scale. And then when we analytically continue, we'll get time varying scalars whose scale of time variation is the age of the universe. Okay, and so specifically, we don't require any fine tuning. ADS-CFT is telling us that the scale of this second derivative at this point is the ADS scale. Okay, so this is like what I think one of the complaints that sometimes people have about having time-dependent scalars in cosmology is that maybe there's some drastic fine-tuning that you need in order to get that to vary on cosmological timescales. Well, this is just the most natural thing that you could have from the CFT perspective. Okay, and so let's understand then the physics. So what do the scalars do in these solutions? So in the wormhole solution, okay, so phi equals 0 corresponds to the unperturbed CFT. So we imagine that you have at the two boundaries, just phi sitting here at the origin. And then, so there could be a solution where phi just remains 0 throughout the space-time. That would be one solution. But then more general solutions will have some derivative for phi going away. And so in the wormhole, what happens is that it starts at 0, it goes down to some point, and then it goes back. And so the solutions generally, you could parameterize them by what is the value of the scalar field in the middle there. Once you analytically continue things to the cosmology, okay, because T goes to I tau, and so starting from this middle point, if the scalar field is going this way in the wormhole, it goes the other way in the cosmology. Okay. And so the analytic continuation of the solution to the cosmological solution looks like this, where you start at a large value of the scalar, it evolves down, goes up to this point at the middle, and then it's time symmetric, so it goes back. Okay, so that's what your scalar looks like in a typical solution. And so what does that mean? So it means that despite the fact that we're talking about a negative cosmological constant theory, okay, that means that this point is less than 0. Okay. For the first while in the cosmology, the scalar potential is up here above 0. Okay, so for the first while, the cosmological constant doesn't matter. It's just usual radiation matter cosmology. But when that radiation and matter dilute and the cosmological constant starts to become more important, then generically, I mean, not always, but without any fine tuning, that scalar potential could be positive, and it can lead to some phase of acceleration while the scalar is still descending down to the negative region. Okay. Eventually, the scalar decreases below the axis here. The cosmological constant turns around to become negative, and you'll get the recollapse.
But there's an interesting point where it's actually 0. Right?
And then, yeah, there's some point where it's 0. And so this was pretty surprising, and in a sense, what it means is that even though lambda is negative in these models, well, we shouldn't immediately discard them for actual cosmology, because apparently the generic solutions can have accelerating regions. So maybe we're in one of these cosmologies where there was a big bang and the scalar's been descending, and
But that is fine tuning, though, to say that that's where we are. Isn't that fine tuning?
well, I mean, I don't think it's fine tuning. Like we're observed, like we have to come up with a mathematical model that has an accelerating phase of cosmology.
Okay.
And so I think what most people sort of jump to is just saying, we see acceleration, therefore lambda is greater than 0. And so we go with lambda CDM and we try to take that as the standard model of cosmology. But I would say this is saying that if you thought about lambda less than 0 cosmology, as it appears from this quantum gravity construction, then most of the examples have time-dependent scalar fields. And many of the examples have an accelerating period. And so if you said, okay, what theoretical model should I use to explain the acceleration? Then I think, don't jump immediately to lambda greater than 0. These are interesting too. So of course, this is like the quintessence.
Right. I was just
This
gonna
is
say,
the
doesn't it sound
quintessence
like
model
quintessence model?
of dark energy, just a particular variant where eventually the scalar field goes to a negative potential.
And this is very much, I mean, because it looks like quintessence, it's completely consistent with a dark matter dominated, more of a physical universe cosmology, right?
Yeah, I mean, I think you can, this is. Let me get to the one more thing that I wanted to say. So, yeah, I mean, I was pretty surprised by this. I mean, it seems to suggest that. So, one of the things, if this is really the explanation for acceleration, then I think what has to be true is that there's like also generically the dark energy is changing by a lot. And so when we saw this, I thought, well, aren't we pretty sure that the dark energy is like pretty constant based on observations? And so I was actually motivated with one of my students to look at the supernova data, like the current data sets, and understand how do the data constrain this picture. So if we just kind of zoom into the vicinity of the present day, if this is the scenario, then maybe we could tailor expand the potential about the present value and approximate it by a straight line. And so consider a model with just these parameters. And so I just wanted to see, what are the constraints if you take the scalar model and it's decreasing like that. And so we just did the same analysis this is the Pantheon Plus survey. We just did exactly the same analysis, kind of repeated their results for WCDM and so forth. And said, okay, what are the constraints on these parameters? And so what we find is actually there's tons of room for a large variation in the scalar potential. So if you look at the models that accurately fit the data, I mean, first of all, lambda CDM is kind of out on the outskirts of this parameter space. The typical models that provide a good fit have like a 100% change in the amount of dark energy over the period where we have the supernova data. So of course, this is just one data set, and we should look at baryon acoustic oscillations and understand how this fits in with CMB and all that.
So this directly implies a W of Z, right? You can predict that.
These different models,
right?
These are not very well modeled by W model. Like some of these models that fit the data well, W does this, and so it's not really accurately captured by some of the parameterizations that people often use in cosmological fits.
Can you explain why there is an asymmetry? Because either way, if V1 is positive or negative, potential goes negative.
Yeah, so I am
We define
good
the direction somehow.
Good question. Yeah, so right. So I think the current value, so if we say that, yeah, sorry. Blackboard. So yeah, I think if I'm remembering correctly, I mean, there's a current way that the scalar field is changing.
Yeah, but your fit doesn't know it. I understand that's the idea you have in mind, but there's nothing, you've done something in your fit, I'm trying to picture what you did. That shows the direction.
Maybe we should
Right.
let Mark finish.
Yeah, maybe I'll
and then
finish.
we can
There's a
do
good
the
answer to
question
this
after.
question,
Yeah.
which I should just postpone for. Yeah, okay, so this is basically, there's some other interesting things about this kind of model. Like if you have this kind of model, there's no cosmological coincidence problem. Another thing in this kind of model, you just automatically from this picture, you will have correlators that observers will think have a horizon problem, but they're just natural because there's like a CFT that is computing those correlators for you. So that's sort of something interesting. And so I think the things, okay, I don't know if this is going to be realistic, but the things I want you to take away from the talk is that number one, if you want to understand cosmology from quantum gravity, from holography, then I think looking at these lambda less than zero cosmologies would be a better place to start, or a great place to start, maybe rather than jumping right to lambda greater than zero. In these lambda less than zero models, it seems like there is some underlying CFT physics because the Euclidean continuation of the spacetime has these asymptotically ADS regions. So it suggests that there's some kind of Euclidean asymptotically ADS spacetime that you could describe holographically, and then you would get your cosmological observables from that. And then there was this interesting point that maybe you could actually generically get acceleration from these models. So maybe they're not as unrealistic as you thought they were going to be. And maybe that's a lesson for quantum gravity in general, that if these models that I'm getting, so this is the only way I know to get a cosmology model out of quantum gravity, and it seems to have these scalar fields that vary on cosmological timescales. So maybe that's a generic feature of cosmology regardless of the model. And so maybe that motivates, like, not immediately jumping to the conclusion that it's finely tuned to have time-dependent scalars. Okay, thank you. Yes. Yeah, so I jumped over that. Yeah, so what do you say about the cosmological constant here? And so in ADS-CFT, there's an understanding of this cosmological scale divided by the Planck scale. That's if that could be a big number, but we know what controls that number in these constructions, and it's just like the number of degrees of freedom of the underlying CFT. Okay, and so instead of it's a very different picture from if you have this bubbling multiverse, and there you're saying, well, all the possible values of the cosmological constant are realized somewhere, and then we're living in some region where you have a small one because of anthropic reasoning. Here, you just have to specify the model that you're starting with. Okay, you have to write down this mathematical model. You have to say how many degrees of freedom does your CFT have, and then in order to get a small cosmological constant, you would need to have a very large number of degrees of freedom. And so the answer to why is the cosmological constant small? It's kind of like I was thinking, if you're like a Minecraft character and you wondered, like, why is your Minecraft universe so big? Well, it's because there's like a large number of bits in the underlying hardware that someone's running Minecraft on. So if someone's like running the universe on a CFT, I guess they shelled out for a really big one. Another question.
I had the exact same.
Oh, okay.
I think we can end here. I think Mark.
Okay, yeah.
And we will be taking Mark to dinner. As last time I checked, there was still one spot left. So if you want to go and be quick.